5, 4, 3, 2, 1. We have ignition and liftoff of a Delta II rocket carrying NASA on an Odyssey back to Mars.
Stage system's looking good. Load release kick rate is in. Vehicle is responding.
Hello everybody, welcome to our program. My name is Claudia Alexander. I'm going to be your host for today. What you just saw was a shot of the rocket launching the Odyssey spacecraft on its way and speeding it towards the planet Mars. Our program today is going to be focused on the Odyssey mission and in a more general vein, what NASA's overall goals are for the exploration of Mars. As I said before, my name is Claudia Alexander. I'm a planetary scientist here at JPL, and it'll be my pleasure to guide our discussion today. Joining me is Mr. Roger Gibbs, the spacecraft manager.
Hello there.
And Dr. Jeff Plout, the deputy project scientist for the mission. In addition to discussing science and the spacecraft with these two gentlemen here, we've also received some email questions from you, our audience, and it will be our pleasure to also walk through some of those questions as we go through our discussion today. For example, many of you were interested in the recently released new picture of the face on Mars, the famous face. Here's a shot of it. We'll talk a little bit about that new image and a little bit about life on Mars and the water of Mars and other things as we go through our discussion today. So let's go straight to some questions about what's actually happening on the spacecraft right now. I'd like to start off by asking Dr. Plout, why Mars? Why is Mars so important to us?
Well, Mars is one of 3 planets in this region of the solar system where we live. Venus, Earth, and Mars all have many similar characteristics, but they're very different in their own ways. And Mars is different in some very interesting ways from the Earth. It has an atmosphere, but it's very cold and dry. And what we're trying to understand with the Odyssey mission is what is the surface of Mars made of, because that's going to take us a long way to understanding how the evolution of the Earth and the evolution of Mars went down different paths.
Okay, so now let's ask Mr. Gibbs, where is the spacecraft right this minute, and can you tell us what it's doing right now?
Well, if I could have the first view up of the spacecraft configuration, it shows what the spacecraft, it actually shows what the spacecraft will look like around Mars. It's pretty similar right now. Where it is right now is on its way to Mars, obviously. It was launched on April 7th. It's about 1/3 of its way there. And what we've been doing up to now is checking things out. It's working very well. It's working very, very well. Hopefully that will all continue. And we're preparing for the next steps in our mission. The second view is up, and it's of the spacecraft trajectory. And when that launch vehicle shot that we showed at the start of this program left Odyssey on its way to Mars, it's going to be now on an orbit going around the Sun between the Earth and the Martian orbits, and we get to Mars and we stop there.
Cool. Let's see, we have a question from Ben in the 12th grade from Minnetonka, Minnesota, and he was wondering, how does NASA communicate with the Odyssey orbiter, and how do you know it's working?
We use radio. We use a radio system. We have an onboard. We actually have a couple of onboard radio systems, but we have one for communicating with Earth. We have several Earth-based stations, and what we do is we take the temperature, the pressure, a number of software telemetry channels, and we're able to ascertain the health of the spacecraft.
So it's kind of like having a patient on a surgery bed, and you hook them all up with the sensors all over his body, and you can kind of read what's happening.
That's a good way to look at it. Some are more critical than others, but we're looking at them all.
Okay. And so your report is that Odyssey's working fine right now.
It's working very well.
Very good. For the benefit of our audience, are there humans on this spacecraft?
This is no. This is a robotic spacecraft. It's a robotic spacecraft. You know, the basic box structure in the view earlier, you could see the basic box. It's not a whole lot larger than the span of my arms. It's exciting mission, but does not have people.
And wouldn't you say it probably would be quite a long time before we're actually going to be able to send people to Mars?
You know, looking at what we had to do to get this relatively small robotic spacecraft to Mars, it's a very large and very significant endeavor to get people there safely and get them back.
Okay, so it'll be a little bit longer before we're able to answer that question with a yes.
That's right.
Okay, so you're speeding along through space, and then what's next for the spacecraft?
Well, as I mentioned, the launch vehicle left us on a trajectory circling the Sun, going between Earth and Mars orbit. On October the 23rd, we will get to Mars. We approach it at a high velocity. We'll come around the backside. We turn the spacecraft around, burn the main engine for about 20 minutes to slow us down enough to get us into orbit around Mars. It slows us enough that we are captured by the Martian gravity, thank you. And we are then in a relatively large orbit, comes in close, goes up far, and we then go into about a 2-month period of aerobraking where we use the atmosphere of Mars to slow us down using the solar arrays as air brakes. Not a whole lot of force on any one orbit, but small amount of force. But over 2 months, we slow down so that the elliptical orbit eventually gets in and we are in a circular orbit around Mars.
Let's see, we had a question from Portugal. Tiago Hormigo of Portugal wrote to ask, how do you engineers at JPL figure out the density of the Martian atmosphere that's used for this aerobraking activity? And that density does change with time, so how do you work with that?
You know, that's a really good question. We cheat.
No!
Originally, the scientists will look at obscurations of moons and use telescopes and estimate the atmosphere, but the United States sent Viking to Mars, and we were able to get...
That was in the 70s?
That was in the 70s, and they actually went through the atmosphere and they take measurements, and so there are measurements that we have. We have the Mars Global Surveyor, which has been at Mars now for about the last 4 years, and it went through an aerobraking phase, and it has instruments to measure the atmosphere, so we have actual measurements of the atmosphere. It's a good question. It's critical that we understand the atmosphere well. We'll be using instruments on the MGS, the Mars Global Surveyor, and instruments on our own spacecraft to determine the temperature of the atmosphere that gives us the height and the density.
That's great. It's a little bit like predicting the weather, isn't it? Because the atmosphere will expand and contract based on what the sun is doing at any given time.
I mean, it's very true that our mission success depends upon understanding the weather around Mars.
Let's see. Another question from Greg Schwartz. Once we get in orbit, and I assume we mean the circular orbit, how high will we actually be over the surface of Mars?
It's a 400-kilometer or about a 250-mile above the surface orbit.
Okay. We have another question from Slovenia. First of all, let me ask, is this spacecraft going to land on the surface of Mars?
We go into orbit, and we have a several-year orbit around Mars, and then we raise our orbit to ensure that for at least the next 50 or 60 years it will never land.
Okay, and our question from Slovenia is that the lander part of this mission was actually canceled. So will the orbiter be able to, you know, achieve all the original scientific goals?
The scientific goals for the Odyssey program were divided into orbiter and lander objectives. The orbiter will conclude with meeting all of its objectives. The lander objectives will not be met by the orbiter, but what we did do was take this opportunity to refocus our attention to the orbiter to make absolutely certain it's going to work. And NASA has on the books plans for future missions for landers that are more capable than the one that we had on the books, so they'll capture all that science data in the future.
Great. Now I'd like to ask, now Odyssey, being an orbiter, is going to be joining Mars Global Surveyor, which is already in orbit around Mars and has been, as you mentioned, in orbit for about 4 years. How does this mission, the Odyssey, differ from Mars Global Surveyor, the earlier mission?
Well, what we've done in designing these missions, the sequence of missions to Mars, is we try to build on what we've learned so far and then try to enhance our understanding by sending in new instruments that complement the information that we've already acquired. So the Odyssey has several instruments that are focused on answering the question, what is Mars made of? What is the composition of the materials at the surface of Mars? So far, we've gotten a great deal of data about the surface topography. We have many, many images of the surface at high resolution, but we still are only beginning to understand what the surface is made of. So we're kind of filling in that gap in our knowledge by sending these new types of instruments to understand the surface composition.
Okay. Let me just go over that again, because we did have a couple questions from Tim Mitchell of Huntsville, Alabama. And the MGS had a camera, and the Odyssey mission will have a different suite of instruments. Maybe you could tell us a little bit about what the mission of Odyssey is and some of the instruments, the new suite that it will carry.
Okay. The Odyssey spacecraft carries 3 sets of instruments, 3 instrument packages. Two of those are for the purpose of looking at the surface of Mars to understand its composition. And the third one is a radiation monitor, and that one's called MARIE, the Mars Radiation Environment Experiment. And the purpose of that is to measure the particle radiation that may be a hazard to future astronauts during a manned mission some decades hence. The other two instruments, one is called the Gamma Ray Spectrometer, or GRS, and the third is the THEMIS, the Thermal Emission Imaging System. Those two instruments are using different approaches to understand and map the composition of the surface materials. Now, THEMIS is a camera system, and so it will be taking pictures both in the visible part of the spectrum, but especially of interest is in the infrared part of the spectrum, a part of the spectrum that your eyes cannot see.
And that's actually not a part that Global Surveyor is capable of at this point.
That's right. What the THEMIS does is it captures images at a rather high resolution in the thermal infrared, whereas an instrument on Mars Global Surveyor called TESS was looking at much coarser resolution, much larger pieces of terrain in a different way.
Interesting. I think we'll come back to that point of resolution a little bit later in the program. Let's see, I'd like to ask how Odyssey will look for water, and we also have several questions from our viewers about that. So we have some questions from Rex Garns and Greg Schwartz about how can the spacecraft locate and tell the difference between water that's on the surface and water that's under the surface of Mars.
The Gamma Ray Spectrometer suite of instruments has three different components, and all of them are sensitive to the presence of hydrogen in the soil in about the upper meter or 3 feet or so of the soil. Now, hydrogen, of course, is a component of water. So we believe that by measuring the hydrogen abundance, that's going to be a good indicator of where water ice may be located in the soil. Now, whether that water ice is right at the surface or somewhere within that first meter is something that actually we're going to be able to make an estimate of by comparing these hydrogen measurements between the three different instrument packages on the GRS system. Now, we won't be able to see water any deeper than about a meter or so. So we're really just looking at that near surface package of soil.
We have a question from Joshua Morrison wondering if you can find hydrogen. How do you know that hydrogen is actually associated with water and not some other compound like methane or something else?
Well, that's an excellent question. And certainly hydrogen is present in our solar system in many forms. It could be free hydrogen. It could be bound to oxygen in the form of water. It could be bound to carbon, as you mentioned, methane. It also, hydrogen is present in certain minerals, in clay minerals, for example. So we can't, at the moment, rule out that hydrogen may be in some other form in the soils of Mars. But what we can say is we know that there is water, H2O molecules at Mars. We know there is water vapor in the atmosphere in sort of trace amounts. We know, because we've directly measured water ice in the surface at the polar region, in the north polar region of Mars, and up to this moment, that's the only form of hydrogen that we've actually measured at Mars. So our going-in assumption, which we'll have to verify with these measurements, is that most of the hydrogen in the soils of Mars is probably in the form of water.
Cool. Let's see. You talked about being able to measure the elements and minerals, and can you tell us what's the difference between those two, and how will the difference, what will measuring those differences, what will that tell you?
Well, we're taking two approaches to measuring the composition of the surface. As you mentioned, one approach is to measure the elements, and those are the atoms, the atomic elements on the periodic table, things like iron, magnesium, carbon, oxygen, etc. The other approach is to look at the minerals. Now, a mineral is a combination of elements in a certain crystal structure and certain combination, and examples of minerals are quartz and feldspar and salt crystals and things like that. Those are all minerals. So the GRS, the Gamma Ray Spectrometer, is looking at the elemental composition. The THEMIS, the thermal system, the imaging camera, is looking at the mineral composition. So we're taking those two approaches, and both of them are really unprecedented. They're going to give us information about the surface composition of Mars that we've never had the ability to acquire before.
Can you tell us a little bit, using these rocks here, what those differences are going to help you understand about maybe the science of Mars?
Okay, well, let me first show you a picture that was acquired from the Mars Global Surveyor. And this is a high-resolution image of an area on Mars that shows layered outcrops. In other words, hillsides where we see striped rocks. And this has been really a remarkable finding from the Mars Global Surveyor, is that in many, many regions of Mars we see these layered rocks. Now the problem is we don't understand how those layers formed. And there are several geologic processes that can form layered rocks. If you look at the rocks on the table here, we have two examples of layered rocks. One of them is formed by a water process, sedimentary rock, in which clays and muds are laid down layer by layer, and eventually that turns into a rock. The other one is a volcanic rock, in which layers of volcanic material, probably ash that comes out of a volcano in big clouds, piles up in layers upon layers. Now, if we just had a picture, a black and white picture, or a visible light picture like we just saw, you wouldn't really be able to distinguish what process formed those rocks. However, with the Themis instrument, we're able to measure the composition of those rocks. And there are certain rocks that can only form that particular composition in a watery environment, whereas others are most likely to form in a volcanic environment. Now, let me show you an example of the kind of images that Themis will be acquiring. This is an example taken from orbit around the Earth, an instrument called ASTER. It's very similar to the instrument Themis. And this is an area of the desert in California here, near the Sierra Nevada, kind of between Death Valley and Sierra Nevada. And on the left is kind of a black and white picture, what your eye would see, or maybe what the mock camera on MGS would see. On the right is an example from ASTER of what Themis will see. And you see all those different colors. Those colors are directly measuring the composition of the surface materials. The reds are quartz-rich, the blues are iron-rich, the greens are carbonate-rich, limestone rocks. And so we're going to be able to have images that show the mineral composition, and that will really help us understand how these layered materials formed and whether water was part of the process.
Boy, that's very powerful, very interesting. Let's see, we had a question from Jorge Eduardo Velasquez, who wrote to know if Odyssey will measure the existence of things like gold, silver, diamonds, petroleum, and other precious metals, and then if that's possible, who would own those? So I'm going to give you the opportunity to answer the first part of that question.
Okay, the first part is that if any of those elements, such as gold or silver, are present in large quantities, we might actually be able to detect them with the gamma-ray spectrometer. However, we don't really expect any of those elements to be present in abundance. What we're really looking at are the most common, what we call the rock-forming elements, and those are oxygen, iron, magnesium, potassium, calcium, carbon, etc. Those we know from our previous measurements that they're likely to be there in some abundance. If there are those precious metals there, in any particular abundance, we might see them. And exactly who's going to own them, maybe you know the answer to that.
Well, actually, we had to go look that up. And there is a United Nations policy which the United States has signed on to, which states that no country may claim sovereignty over any objects which are in space. And so that basically means that that NASA will not be able to lay claim to any silver veins or anything that might be discovered on Mars. I want to go on and talk about the water of Mars in a little bit more detail. One of our viewers, Amadeo Fazzolari of Melbourne, Australia, was wondering, is it possible that the scientists, are searching for water on Mars, and for example, I think this is an image from the camera of Mars Global Surveyor showing some gullies and so forth. Is it possible, how do you know that those gullies were actually formed by water and not some other substance? And are the geologists using Earth too closely to study Mars, and are they drawing maybe conclusions that are based on or prejudiced by our knowledge of Earth?
Well, that's an excellent question, and the blunt answer to that is we don't know how these gullies formed. We don't know how the channels formed on Mars. And that's one of the reasons we're sending this particular set of instruments to Mars, is because we will be able to identify the fingerprint of certain kinds of minerals that can only form in water, and that will help confirm the origin of these channel-like features and these gully-like features. But again, as with the case of whether hydrogen exists as water ice, the bulk of the evidence, the weight of the evidence that we've acquired so far really points towards water for carving some of these small gullies that we're seeing in the images, in the high-resolution images, and also for carving these much larger channels that are shown in this topographic image, which are the massive outflow channels that apparently burst out of cliff sides and traveled for thousands of kilometers carrying material and carving canyons. Now it's possible that some other agent acted to carve those out. Right now our best guess is it's water, and I think we're going to be able to confirm that hypothesis with the data from this mission.
Wonderful. Let's see. Let's go on now and take some more general questions about Mars. There were some questions, a lot of questions. The bulk of our questions had to do with the famous and so-called face on Mars. This is a recently released new image of this object. And so the question that the viewers have is, is a face really there? And I'll ask you that question first, and then a follow-up question after that.
Well, let's see. That image was a Viking image. And
the original
image that started all the excitement, and a lot of people got excited because they thought they saw evidence of non-natural processes, some kind of living organism creating a monument there. The Mars Global Surveyor has a camera, the Mach, and its resolution is about the span of my arms, as opposed to, I think, 50 meters was the resolution per pixel for the Viking. And it came up across that image at a different time of day. And so Viking came by with a camera with a resolution of 50 meters per pixel. A certain time of day, certain shadows. MGS came by with a different picture. And if you look at this now, you say there are natural processes. There's erosion. There is, whether it's wind or water erosion, there is erosion, and it's a natural process.
Well, now, one of our viewers was wondering, the difference between this picture and the original 1976 picture is so striking, and you had mentioned that it seems to be a naturally eroding feature of Mars, but it seems like there's a lot more erosion that happened between now and that original picture. How is that possible? And could you address that comment?
Well, we have higher resolution, and it's a different time of day. Jeff just showed a couple of images of an Earth-based site where we had different resolutions, and they look markedly different. And you might not even be absolutely certain they were the same. We know they were. The difference of resolution can make things look a lot more detailed. Can make them look different.
Yeah. I think actually that might be even one reason why we send what might seem to be redundant instruments to a target. Once there's greater resolution, it can completely change your impression of what a thing is, or some sort of scientific measurement that is made even.
Well, that's right. That's right.
Let's see. There were a lot of questions about potential life on Mars, and I'd like to go through a couple of those. We had a question that noted that scientists often speak about prerequisites for life, water and oxygen, etc., and they apply those prerequisites from everything on Earth, from bacteria on up. And is it possible that life on Earth requires water and oxygen because those are the things that are available on Earth, and life on Mars, because there are different things available, might take a completely different turn and be a completely different life form? Can you address that question?
Well, clearly that is possible. What the Odyssey mission is going to do at Mars is basic science. We're going to understand the presence of water and weather and geological formations and understand a bit of the history of Mars. We're not precluding looking for any kind of scientific exploration or any form of life. What we're trying to do is do basic understanding. Water is clearly something that's a part of life here on Earth, and understanding the water history of Mars is very important. It's a incremental step in understanding Martian environment. That's right.
Along those lines, Mark Elowitz wrote to ask what effect might the lower gravity of Mars, seeing as Mars is such a much smaller planet than Earth, what might the lower gravity of Mars have to do with potential Martian primitive life forms?
Well, there are a lot of aspects of the Martian environment that are different than the Earth environment, and one of them is certainly the gravity, and that's certainly a factor when we're trying to understand how life might have evolved on Mars. We can't really rule out some kind of life form that's completely different than what we understand on the Earth. In fact, it would be surprising if the life forms if there are life forms on Mars that we find, it would be surprising if they were very similar to those on Earth. But right now, our going-in position is that we're going to try to search for things about life that we understand from life on Earth. And if all of those kind of come up negative, then we're going to have to maybe expand our search and look for different possibilities.
We've got just a few minutes left, and I wanted to address some of the questions related to the human habitability of Mars. We got many questions from Osaka, Japan, and one also from Penn State University. And I think I just am going to have time to go with the one from Penn State. What will this Odyssey mission accomplish with regard to furthering the chance of people landing on Mars?
Well, we have a specific experiment on this mission, the MARIE, the Martian Radiation Environment Experiment, that is designed to measure the hazards posed by radiation for a possible human visit to Mars. In this case, we're going to be, and we currently are, measuring the radiation between Earth and Mars, so on the trip to, and also it would be on the trip back for the astronauts. The particle radiation from the sun and from cosmic rays, and how those, the flux of those particles would affect human tissues. Once we get into orbit around Mars, we're going to be monitoring that to get an idea of the amount and how that might change over the course of a Martian year. So we are actually laying some groundwork, some direct groundwork for human exploration that may follow on in the next few decades.
Are there any how many years do you think it might be before we'll be ready to have colonists landing on Mars?
Well, right now the major issue is how do you keep the astronauts safe on this long, arduous journey. It will be nearly a year in each direction, plus they have to spend some time when they're at Mars to wait for the planets to come back around in position. So really the major challenge is to maintain a safe environment for the astronauts. Technologically, of course, we put humans on the moon back in 1969, which was quite a while ago. So a lot of the technological aspects we probably could get a handle on rather easily, but the fact that it's such a long way away changes the whole equation, and that means probably several decades before we could realistically expect humans to walk on the surface.
That's great. Something that perhaps this teacher's students might be an engineering challenge for them, perhaps.
That's right. That's
Yeah.
right. We're trying to get those students, those
do.
young
You don't wanna
engineers
solve all the
interested
questions
right now. Yeah.
Okay, I think we're pretty much out of time, so we're going to wrap up. The next big step for the spacecraft will be
October 23rd, we go into orbit.
okay, and so hopefully we'll have a chance to bring this webcast back to you with more discussion about Mars once we've achieved orbit insertion. Thank you, gentlemen, both.
Thank you.
Here.